Right, hello Year 11. You should have done your assessment yesterday. Today is going to be the test review. Now, this assessment had a lot of calculations in, but if you knew your equations, the calculations were pretty straightforward. If you didn't know your equations, you would have been very stuck. But if you Googled them during the test, that's absolutely fine. It's better to get the practice in with the equations than just not being able to do anything at all. So, question 1. This is a thinking distance, stopping distance question, and it's mostly common sense, right? So, if the brakes in the lorry are poor condition, how will that affect the thinking distance? Well, if the brakes are in poor condition, that will not affect the person inside if he sees something and presses on the brakes. Okay, so I'll get my green pen. Thinking distance will stay the same. Stay the same. Remember, thinking distance is only changed by distractions or alcohol or stuff like that. The braking distance will increase, okay? If the brakes aren't working as well, it will take longer for the lorry to stop. So B, using a handheld mobile phone while driving is illegal in the UK. The table shows the effect of using a mobile phone on thinking distance. So not using a mobile phone is only 19 meters. Using it with hands free is 23 meters, and using a handheld mobile phone is 27 meters. Okay. Explain why driving using a handheld mobile is more dangerous than with a hands-free, and it says here use data from the table above. If it ever says that, that means at least 1 mark is reserved for data. So let's have a look then. Well, the thinking distance is increased, okay, isn't it? So I'm going to say thinking distance, or you could say reaction time is increased. Thinking distance increases when using any mobile phone. Using any mobile phone. Okay, that would be 1 mark. So that's this top one here is not a mobile phone. The bottom 2 are a mobile phone usage, and you can see the thinking distance has gone up. Now, let's compare hands-free to handheld. Well, if you have got if you're holding your mobile phone in your hand when you're using it, you have a longer thinking distance than if you've got a hands-free kit. So, handheld mobile increases thinking distance more than hands-free. So that'll be 1 mark. Now, this is your opportunity to use data. Well, how much more? 23 meters to 27 meters, that's 4 meters more. So, by 4 meters. So there's your using the data mark, okay? Even if you said just this one sentence here, handheld mobiles take 4 meters longer to stop than a hands-free mobile, that would get you 2 marks. Then the last point, just stating the obvious, so the overall stopping distance increases. Now, why do we have to say this? Because here in the question it was talking about thinking distance, right? You're demonstrating the knowledge that this links to the overall stopping distance, okay? Because remember, your stopping distance is the thinking distance plus the braking distance. So, 1 mark. Thinking distance increases using any mobile phone. 1 mark for saying that handheld increases the distance more, but you get an extra mark by saying more by 4 meters. So the overall stopping distance increases. Okay. A high-speed train accelerates at a constant rate and in a straight line. The velocity of the train increases from... where is the... There we go. Increases from... Sorry, just want to get my highlighter. There it is. Increases from 30 meters per second to 42 meters per second, and that takes 60 seconds. Calculate the change in velocity. Okay, so be careful about that one. So the change in velocity, well, I just need to look at this one and this one. How much did it change by? Well, it went from 30 to 42, and that's 12. So that's 12 meters per second is the change in velocity. Now, use this equation to calculate the acceleration. Well, let's have a look. Acceleration equals change in velocity. Well, we've just said that's 12 divided by time taken. Well, the time taken was 60 seconds, wasn't it? 12 divided by 60. Now, hopefully you used a calculator on your computer, or if you have a calculator actually with you, which I do, I'm going to type it not on my calculator. So 12 divided by 60 equals a fifth, and that is 0.2. So that equals 0.2. Now, what is the unit? That is the unit there. So if you circled it or you wrote meters per second squared, then you got both marks. 1 mark for the 0.2, 1 mark for meters per second squared. Now, part B. Which one of the graphs, A, B, or C, shows how the velocity of the train changes as it accelerates? Now, we know in the question that the velocity increased, okay? So from the question we were told the velocity of the train increases. Let's go look. See, a high-speed train accelerates from 30 to 42. So we know it absolutely cannot be this one, because if you look, the velocity stays the same. Now we have to decide between B and C. So if you are unsure which graph it is, you have a 50-50 now. You've eliminated A, which it absolutely cannot be. So you're giving yourself a better chance. But I'm going to go back to the start of the question. Both of these have the velocity increasing, but B, the velocity seems to be increasing at a constant rate, and C, the velocity increases as a curve, which means it gets faster over time. The acceleration increases over time. But in the question, it says the train accelerates at a constant rate, so it must be B. So it is graph B. It has to be this one. Question 3. The manufacturer of a family car gave the following information. Mass of car is 950, so I'm actually going to write these down here. M equals 950. 50 kilograms. The car will accelerate from 0 to 33 meters per second in 11 seconds. Okay? The time is 11 seconds, and we've actually got the equation for this on the other page. So let's actually scroll back up and have a look. Oh, acceleration equals change in velocity divided by time taken for change. So what was the change in velocity? Well, that was 0 to 33, so it was 33 meters per second. That was the change in 11 seconds. So A equals change in, so I'm going to put delta V just to save writing. That just means change in velocity divided by time. That equals 33 divided by 11, and that should be 3, but I'm going to put it in my calculator anyway, just in case my brain's not working, and it is. That equals 3. Now, make sure you put the unit, because we've got 1 mark here for that, but we need the unit for accelerations. That is meters per second squared, and that is the second mark. Well, we haven't used mass yet, so that's interesting, but let's carry on. And if we look here, it says calculate the force needed to produce this acceleration. So this mass and force. So now we've got force, we've got mass, we've just calculated acceleration. Hopefully those 3 things jog your memory and you know that you need Newton's second law, F equals ma. Force equals mass times acceleration. So if I'm calculating the force, I don't need to rearrange. I just need to go force equals the mass of the car, which was 950, times by the acceleration of the car, which equals 3. So 950 times 3 equals 2850. 2,850 newtons. Notice that there's 1 mark for the number and there's 1 mark for the unit. Now, just be very careful. Usually it will specify, give the unit in the question, but if it doesn't, you should always put them anyway, because you might pick up extra marks like this. So even if you did not know how to calculate acceleration, but from before you knew the unit was this, you could just write that unit down and get a mark. The same here. If you did not know how to calculate the force, but you knew the unit was newtons, you could just write newtons and get a mark. Okay. The manufacturer claims the top speed of 110 miles an hour. Explain why there must be a top speed. For 3 marks. So, hopefully you know that as you get faster, air resistance increases. I don't know if you've ever been in a bike or in a car, stuck your hand out the window, or you can feel it as you pedal faster, right? On your bike, you have a top speed because you pedal. As you pedal, you can feel the wind blowing you. That is actually just air resistance, okay? So you pedal faster, air resistance gets harder to push against, and eventually the two forces will balance out. So, as you get faster, drag forces, I like to call them, but just so that we know what we're talking about, I'm going to say air resistance. If you said drag increases, that would be perfect, and that's something I would write because drag is a lot easier to write than air resistance. Resistance increases. So as you get faster, air resistance increases. Now, so let me draw a little diagram actually here. So here's my bike. I'm pushing as hard as I possibly can. So that's my force. Maybe it's 100 newtons. To start off with, air resistance is maybe only 10 newtons. But as I get faster, it becomes 20, 30, 40, 50, 60, 70, and eventually the air resistance equals 100 newtons too. Now, I can't push any harder because I'm already pushing as hard as I go. What happens is I reach my top speed there. I am now moving at a constant speed, and that is my top speed. Okay, so as you get faster, the air resistance will increase until air resistance force, the air resistance force equals the push force. Like I've got in this top diagram here. When the air resistance force equals the push force, you have reached you are in equilibrium, so you've reached your top speed. Now, you need to say that either the resultant force is 0, so the resultant force equals 0, or you say the acceleration is 0. There you've got your 3 marks. Question 4. The diagram below shows a moving tractor. The forward force from the engine exactly balances the resisting forces from the tractor. On the tractor. So what it's saying here, my tractor, forward force exactly equals the resisting force. So what is the motion? It must be going at constant speed. The tractor goes to a drier part of the field where the resisting forces are less. If the forward force from the engine is unchanged, how, if at all, would the motion of the tractor be affected? Well, now it said the driving force is still the same, but the resisting forces are less. So what happens? The tractor has got to speed up, right? But we can't just say speed up. We've got to say that the tractor will increase in speed. Okay? It accelerates. So the tractor will accelerate Yeah. And if you want to add something on, it will accelerate to a higher constant speed. But we'll leave it at that. Now, let's continue. Part B. Right, ignore the graph. I know many of us won't be able to do the graph. If you were able to print it out and do it, that's perfect. But if you were not, most of us wouldn't have been able to print anything off. I know I don't have a printer, and I can do this because I can draw on my computer because I bought a little tablet thing to write on. But I know not everyone will have that. So if you are unable to do the graphs, that's fine, because you could do it using shapes and drawing the shapes on the graph, but it would take a very long time. So I don't mind if you were unable to do this. So I'm going to skip. We're going to skip the whole question. You can do part D though. Part D is giving you all the information you need to complete the answer, and it says calculate the acceleration. Remember, acceleration equals the change in velocity divided by the time taken. So how long did it take? 15 seconds. The change in velocity was 6. So that equals 6 was the change in velocity. That took 15 seconds. What is 6 divided by 15? 6 divided by 15 equals 0.4. 0.4 meters per second. Okay. Right, question 5. So we've now got a racing driver in what looks to be a bit like a Formula 1 car. The driver pushes the accelerator pedal as far down as possible. The car does not accelerate above a certain maximum speed. Explain why. So we've actually already answered this. Now, let's just say he's got his foot floored to the floored. There is a maximum possible force. Okay, same with you on your bike. You can only push as hard as you can. So there is a maximum force. There is a maximum force from the engine. Yeah. If you wanted more force, you'd have to build a bigger engine, right? Now, like we said before, I'm just going to call it drag this time because I don't want to write air resistance lots. So drag, we're just going to start writing it backwards there. Drag forces will will oppose the driving force from the engine. So I'm going to call the force from the engine the driving force. Drive force. So let's draw my diagram again. The drive force is going to look like that. But when the car's going slowly, the drag force looks like this. As it goes faster, the drag force will get bigger, won't it? So drag forces will oppose the drive force. The drag force will get larger as the car gets faster. Okay. Until they, when I say they, I mean the drive force and the drag force are equal and opposite. That should be enough to get you all 4 marks. You could then qualify as well, saying that means that no acceleration. So, B, the racing car has a mass of that. When the brake pedal is pushed down, a constant braking force of that is exerted on the car. So first of all, calculating the acceleration. Okay, let's have a look at the top. We need to use, so we've got F equals ma. Yeah, that's good. So we've got a force, we've got a mass. So force equals mass times acceleration, right? We would like to find out what the acceleration is. Okay, so I'm going to put them in. Well, the force is 10,000 newtons, which equals mass, which is 1,250 times by acceleration. Now, in order to get acceleration by itself, I'm going to have to divide this by 1,250 and then divide this side by 1,250, which means that these two will cancel, right? So let me type that in. So to get A, I've got, this is what I'm left with, 10,000 divided by 1,250, and that will equal A. So what does that equal? 10,000 divided by 1,250 equals 8. So then I'll have A will equal 8. Now make sure you write the unit again, meters per second squared. There you go. Now part 2. Calculate the kinetic energy of the car when it is traveling at this speed. So kinetic energy, KE, kinetic energy equals a half times by mass times by the velocity squared. So let's put that in. KE equals a half, which is 0.5. Do you know what? Actually, I'm going to write 0.5 instead of a half. Might be a bit easier for when you put it in your calculator. 0.5 times by, what is the mass of the car? Well, the car has a mass of 1250. 50 times by, I'm going to open my bracket now. That is 48 meters per second, but I need to square the 48 before I do the calculation. Because I've got a scientific calculator, I can do it all at once. Well, 48 squared equals 2,304. So just if you don't have a scientific calculator, I'm going to write it all out again. 1,250. Remember, you do your brackets first before you do the rest of the equation. Okay, so you only square the 48, and 48 squared equals 2,304. Now, if I multiply them all together, 0.5 times by 1,250 times by 2,304, I get 144,0000 joules. Now, you get a mark for the unit, okay? So if you just put joules down and your answer was wrong, you still get a mark. Part 3. When the brakes are applied with a constant force, okay, so we've got a force here of 10,000 newtons, the car travels a distance of 144 meters before it stops. Calculate the work done stopping the car. Hopefully we can remember this. Again, lots of equations. Work done equals force times by distance. Okay, well, the work done equals the force, which was 10,000, times by the distance traveled, which is 144, and that will equal 10,000 times 144,000. So 1,440, so 1,440,000. 1, 2, 3. And what is the unit of the work done? That is joules. Okay. And after you've done that, that is the last question. Send a photo of one of your green pen pages and email it to me, and then you are done for today.